this evening to listen to this paper presentation. My name is Tim Hunter. I'm the founder and the developer of the TrueLoad software developed by Wolfstar Technologies. This paper I'm presenting this evening is a paper that I did in conjunction with Will Mars from Endurica. Endurica is the best-in-class rubber fatigue software. And Will and I have been wanting for years to do a project together, and we kind of took this this opportunity with a pandemic to do the project. So you'll be seeing in this paper today, part one, I'll be presenting this live, and then part two, we're going to have a cameo appearance of Will and I working on this project. And there will be like an 8-minute short video at the end showing us doing everything together here on this presentation. So please sit back and enjoy this presentation today, and we'll get right into it. So we've titled this presentation "Spring Loaded: Using Load Reconstruction for Rubber Fatigue on a Pogo Stick Digital Twin, Part 1." You know. Little joke that Will and I talk about with this project is with all the smart minds of the world working on the pandemic and the COVID thing, we had to put our minds together to figure out what's going on a pogo stick. So this is what we did in the lockdown with the pandemic. Just to start off with, you know, digital twins are a big part of what people talk about in simulation these days, and digital twins are an important feature. But there's an issue with them. The traditional digital twin is an open loop digital twin. So this traditional digital twin starts with an open loop. So what happens is that as a designer analyst, you'll say, what parameters do I want to measure? So you might measure a valve opening or a pressure or maybe even a load or displacement. So you'll figure some things that you want to measure in the environment. And then you go to your simulation and you set up basically a state space model where you do a simulation simulating every possible combination of values that you can conceive of having for those parameters that you're going to measure in the real world. So you run thousands of FEA solves to kind of come up and build the state space model. And then when you run the digital twin, then what's happening is the digital twin will take a measurement from the real world and basically just look up results from your pre-solved FEA analysis and present them on the screen. And so you're essentially just creating a cartoon. You're playing a cartoon. And the problem is that with this implementation, is that if something fails in the real world, if a bolt broke, if a member failed, if a valve wasn't opening properly, you would never know that from the digital twin because it would just be playing back a cartoon of results. So with the TrueLoad approach, we have basically what's called a closed loop digital twin. So the TrueLoad technologies, as we'll get into later in this presentation, only measures strains. So we're measuring strain response in the structure in real time. And so we want to measure strains on the structure in real time. And the TrueLoad technology will basically use this correlation matrix that we extract from the FEA model. And we'll basically in real time then take those measured strains and calculate the loads operating on the structure in real time. And then through our technology, then we run that back through the FEA model and we create these correlation plots here. So these correlation plots are plotting measured strains versus simulated strains. And we want to make sure those plots are pretty much staying on the one-to-one correlation line. If anything changes in the structure, if stiffness changes, if there's a failure going on, this correlation plot will start to fail. So now when we generate these correlation plots in real time, now we've got confidence to go in and do things like damage monitoring or generating operating deflection shapes or whatever things that you want to monitor. The TrueLoad digital twin approach is really a closed loop system and gives you very high confidence with what's going on. The traditional approach, you're just making a cartoon and it looks pretty, but it may or may not be what's actually happening in the real world. So with our digital twin application here, with our pogo stick, what we're going to be doing here is we're going to be basically putting on strain sensors on this pogo stick, measuring strains in real time. We'll take that and run that into our server, and then we'll basically in the process we'll calculate loads in real time and run that into the Endurica solver with fatigue life calculations in real time, and we'll generate nice images here on our simulation server, and then we can also then report those back out through our database server out to an asset manager. So you could have a device like a cell phone that you could be displaying the results of this damage in real time. So everything we're going to show you here is something that can happen very much in real time. So with the TrueLoad technology, what we're going to do is we're going to be basically measuring strains on the structure, on the structure in operation, and turn those into forces that we're going to run into our durability model. Okay, so TrueLoad is basically taking any structure, turning it into a load transducer to produce the forces, and in this application, we're going to leverage those forces to drive a fatigue simulation. And here's how it would go. So we'll get the forces from TrueLoad, and then we'll drive these into the Endurica modules here. So this Endurica module here is going to be basically doing some pre-work to set up the results from a nonlinear FEA using their EIE module. And then once we've got that, then we'll run that into the Endurica CL module to calculate fatigue life. Okay. So here we go. Part one with TrueLoad. We're going to do load measurement. So we basically are going to set up a series of unit load cases on the FEA model. So we're going to get a series of loads at the springs on the pogo stick, and we'll get moments coming in from the footboard. So we're going to measure 6 degrees of freedom of loading. We'll go through the TrueLoad technology then. TrueLoad is going to tell us where to place the strain gauges on the structure. So TrueLoad's identifying these little positions and orientation to the strain gauges. And now that we've got that, then we're going to go in and do strain measurement. So here's basically what we're going to do is we're going to basically lay strain gauges on the physical pogo stick. We'll hook it up to our load transducer, and then you'll have your test operator, me, getting on the pogo stick to generate the strain response. And now we'll have these time histories of strains. And now from these time histories of strains, then we'll go through the TrueLoad post-test module, and the post-test module will take the measured strain and turn those into loads, and then it'll generate for us also this nice correlation plot that's showing measured strain versus simulated strain, making sure that we're reproducing the strains properly in the structure. So this is what TrueLoad is essentially doing. Okay. So let's get into the theory. So how does TrueLoad do this? So quite simply, what TrueLoad's doing is we're basically working with linear systems and loads. So linear systems is where loads are proportional displacements, displacements are proportional strains, strains are proportional loads. It's a linear system. Now we fully realize everything in life is nonlinear. Okay, we understand everything is nonlinear, but what we're going to do is we're trying to turn our device into a load transducer. So we're going to target nominal areas on the structure where the strain response is remaining proportional and linear. We'll stay away from welds, we'll stay away from bolted joints, we'll stay away from areas of contact. We're going to be in nice nominal areas where the strain response is going to remain proportional and linear to the exterior loading. The loading can be as nonlinear as anything. The loading could be sinusoidal, ramp loading, even impact loading, like this pogo stick's doing. We can get the strains responses from that to calculate the loads. So I can take this diagram here and just turn it into a couple of equations, okay? So the right-hand side of this triangle, that's F equals Kx. Well, that's Hooke's law. So if your structure is on bulk, obeying Hooke's law, then the left-hand side of the triangle's got to work as well too, which is strain times a correlation matrix is equal to loads. And we're going to calculate loads as being strains from test times a correlation matrix from FEA, okay? This is what's called in the papers, this is called the science of influence coefficients. So if you looked up, if you did some searching for influence coefficients, you would find this equation in there, okay? So we're going to get into this and go into this a little bit more here. So here's our equation. We've got strain times a correlation matrix is equal to load. In this example here, I've got 3 unit loads on my structure, and I've got 4 uniaxial strain gauges laid on my model. So here, each column of the strain matrix, each column represents a uniaxial strain gauge. Let me go through this row by row here so you can see what's going on. So here, if I turn load case number 1 on load cases 2 and 3 off, I can write down the strain responses at those 4 gauges. So I'll record those 4 strain responses at those 4 strain gauges, and we'll go on to the next load. So here I've got load case number 2 turned on, load cases 1 and 3 are turned off, and now at the same 4 strain gauges, I'm going to record the strains, but now the strain responses are different. The strain responses are different because load case 2 is different than load case 1. We're essentially getting the unique strain signature for load case number 2. And now we can go on and go in and turn on load case number 3, turn off load cases 1 and 2, and get load case number 3's unique strain signature, okay? So now we've got 3 unique strain signatures, 3 unique load cases. We've got a well-behaved linear set of equations. This is something we can solve. So let me talk a little bit about these unit loads here for a minute. So these unit loads could be forces, XYZ forces. They could be moments. They could be unit displacements. They could be pressure loads. They could be thermal loads. They could be inertial loads. They could even be mode shapes. So if you laid strain gauges on your structure using mode shapes, a Truler would directly calculate the modal participation factors of those mode shapes. It's a very, very powerful technique for understanding the dynamics of your structures. Okay, so now we've got this nice equation for strain times C is equal to F, and the only thing I haven't talked about here is C. So how do we find C? So if we look at the F matrix here, and if we call turning a load on a 1 and turning a load off a 0, then the F matrix becomes identity. And then I can do a pseudo inverse. So I can take strain times C is equal to I, pre-multiply by strain transpose, pre-multiply by strain transpose, strain inverse, and we get C is equal to strain transpose, strain inverse, strain transpose, and that's what we pull the FDA model. So I know it's late in the evening there, but if those of you who remember back to your linear algebra in college, this is basically the matrix form of least squares fit. We're essentially creating a least squares relationship between strain response and load on your structure. This is really what we're doing here. Okay. All right. So now we've got this great correlation matrix for C, but there are millions of load cases of possible strain gauge locations. So how do we know where the best ones are? What we recognize here is that our correlation matrix, it's got an inverse in here. And inverses can be very poorly behaved, and that's not what we want. We want the best behaved inverse we can get here. So we recognize that the inverse of a matrix is defined by the cofactor of the matrix divided by the determinant. So the thing in the bottom, the determinant, we don't want that to be 0, we want that to be maximum. So our objective function for finding the strain gauges is to maximize the determinant of strain transpose strain, and we do that search with this Galil-Kiefer d-optimal search algorithm. It's a very efficient sequential exchange algorithm for finding the strain gauge locations. And this is how we're doing it, okay? It's a very straightforward technique. It's very robust, and we've done it for lots and lots of customers. So let's get into the pogo stick. So this is me riding on the pogo stick there. For those of you who have never ridden a pogo stick, it's a lot harder than it looks, okay? This is a pretty tough thing to do. So I had to do a lot of practice even to get this far. Here we go. So here's setting up the FEA. So here's my little flow chart on the top of the process here. So here's me setting up the FEA model. I had 6 unit load cases. I put XYZ unit loads at the top of the spring here on the pogo stick. And then down here where the footboards are connecting to the structure, I put in 3 moments there at the footboard connection. And then the way I set up the restraints on the model here is I put restraints down where the spring attaches in on the bottom. So I got XYZ restraints, and I'm just putting some in my coordinate system here, UZ restraints, just to keep the structure from spinning. I could have solved this with inertial relief, but I chose not to. Okay, so just to let you know that as well too, I chose not to do an inertial relief approach on this one. Okay. So this is me setting up the FEA model and basically telling my FEA model which loads I want to learn about. And then I just go into the TrueLoad pretest software. So here it is. This is the basic interface. Basically, we load in the FEA model. We load up all of our unit load cases I just had. I just showed you on the screen. And basically, we just say, go find me some strain gauges. And it draws up the strain gauge locations on the model where they need to be. So this is the basic interface for the TrueLoad pretest software. It's very powerful, very easy to use, and it's very efficient here. And then once we've gotten the strain gauges laid, TrueLoad has got very nice tools in here for doing documentation of the gauge placements, because we've got to put the gauges on physical parts. And so we had to come up with a way to do this. And so basically, this is our gauge dimensioning tool. So you can see where we've laid out the gauges here. And the units on these slides here, these are imperial units. So if, these are not millimeters, these are inches on here. Okay. So here's our pogo stick laid out and the strain gauges identified on them and the dimensions. And then once we've done that, then we just go off and lay the strain gauges on. So I had my colleague Cindy Murphy lay all these strain gauges for me. So she went in and laid the strain gauges on the structure. So you can see here they're wired up, and the strain gauges are wired on here. And we've got all 10 of my strain gauges laid up on the structure here. And now that we've got the strain gauges laid, we just got to set up the data acquisition system. So this is the data acquisition system I'm using. Any data acquisition system works, but this just happens to be the one I use. It's a nice compact system here, this DTS Slice Micro. So it's the system that I had at this point in time had 12 channels, quarter bridge strain gauge channels. And I was sampling at 1,000 hertz. The unit itself has got capability to sample up to 20 kilohertz. And you can see it's about 2 inches square in the base, and then you just add on whatever modules you need, and you can see how nicely it fits onto my pogo stick very, very nicely here. So we've got my 10 channels of strain gauges wired up here, and it's all set to go. And then here we're collecting the strain data. So this is the strain data that we collected from me using the pogo stick. All right. And then from that strain measurement now, we go into the post-test module. Okay, so the post-test module in TrueLoad, basically we load up our TrueLoad file, which has got that correlation matrix in it. And then we bring in the strain data file that we just recorded from test. And then we just tell TrueLoad to calculate the loads. And it's really that simple. There's lots of other buttons here for doing plotting data and mapping and dropping channels, but really this is all it takes, okay? And once we push that button, what's going to happen is TrueLoad is going to take the measured strain data, multiply it by our correlation matrix to generate the time histories of loading. So we're measuring loads at the spring and the moments at the footboard. So we got loads and moments there. And now that we got these loads and moments, TrueLoad automatically in real time now will go back and simulate the measured strains, simulate the strains at the strain gauge locations from the FEA model and plot them against measured. So on the horizontal axis here, we've got measured strain. On the vertical axis, we got simulated strain for all 10 gauges, and you can see how nicely we're correlating to that strain response there. And now that we've got this nice correlation, then we just go into our True QSE tool. QSE stands for quasi-static events, and basically True QSE is a really powerful module for us here that will allow you to go in and load up your results from TrueLoad post-test. So here we've got our 6 unit loads and their corresponding loading functions here. And now we can go in and query anything we want. So we can go in, for example, and query the displacements of the ends of our frame here. So this is querying the XYZ displacements down there. Or if we're interested in the reaction forces here, because this is where we had a restraint, here we're getting the reaction forces here. And these are actually the forces that we're going to drive and send into Endurica, because the rubber bumper is right on the other side of that, okay? And then once we've got all of that information, TrueQSE will allow us to create operating deflection shapes. So here's a nice operating deflection shape of my pogo stick of me while I'm using it, okay? So you can see we're getting structural response throughout the whole structure, and you can see the reaction force as it's going through. And we're doing this. We got highlighted this little peak point in time that we're doing this calculation over. All right. So now we're going to take these reaction forces now and send these off to Endurica, okay? And so really the summary is going to go something like this. Was basically we're getting the strain history we're getting the strain and load history. We're basically going to run that into true load. That's going to go into the Endurica EIE and Endurica DT modules. He's got a nice little screen for us to look at these results in real time, and then we kind of repeat this over and over again. Okay, so basically, this is doing the whole thing in real time. All right, so we're going to now transition off to a video that was recorded with Will and I doing this in real time. So you're going to see some back and forth between myself and Will Mars, and it's about an 8-minute long video, and then that'll kind of wrap up our presentation for the morning here. So let's get right into it. Right.
How you been, Tim?
Good, Willie. How you been?
Good.
How's the quarantine treating you?
Oh, well, I got my wild man look going here. Beard for the first time in 20 years.
Yeah.
Showing a lot more gray than it used to.
Yeah, I stopped growing my beard when it got gray. Okay. Yeah, and I've got the home hairdo right now. So.
Here we go.
Well, hey, Will, over quarantine, I've kind of taken up a new hobby.
Yeah.
Pogo stick. I went out and bought a pogo stick, and I've been hopping around on the thing, and this pogo stick, it's got a rubber bumper on the bottom. It's got on the bottom of the thing. It's got a rubber bumper here.
Okay, that's right up my alley.
Yeah, and I'm thinking, wow, this thing is really going through all sorts of loading and fatigue. It'd be really cool to kind of figure out the durability issues with this little rubber bumper on the bottom of this thing.
Love it.
So is that something you could do? I don't know. Maybe I'm talking to the wrong guy.
Absolutely. No. If you could get me X, Y, and Z loads on the tip of that pogo stick, then I can process those lickety split, and we can give you a dashboard that shows you in real time the evolution of damage on that tip.
You want loads? You came to the right guy.
That's perfect. That's just what we need. Let's do it.
We're all set. So let's go.
This is part 2 of a workshop that Tim Hunter from Wolfstar and I have put together to talk about how you can use load reconstruction, how you can use rubber fatigue analysis tools to build a digital twin. This slide is a summary of the preliminaries that you need to have in place before we can get to the updating cycle for running a digital twin. And so one thing we need, of course, just like we saw on the last slide, is we're going to need the correlation matrix from TrueLoad, right? That relates the strain gauges to the loads and allows us to convert strains that we observe in the strain gauges on the frame to the X, Y, and Z loads. Now, we're going to want to take these X, Y, and Z loads, and we're going to get them converted into strains in the nonlinear tip of the pogo stick. And to do that, we're going to have to somehow involve a fine element analysis solver to make those calculations. But what we're going to see is that the fine element solution is too slow to use in real time. So rather than doing that, what we're going to do is we're going to use a tool called Endurica EIE. EIE stands for Efficient Interpolation Engine. And what EIE does is it allows you to take a set of pre-computed fine element solutions and store them for later use in a very rapid calculation that captures the full nonlinearity of the part and allows you to get the strain tensor components for every element in the model for any combination of the input loads. We'll unpack this a little bit more, but so one of the basic things we'll need is to have run the fine element job that it takes to feed the interpolation process and get that all set up before we get into the digital twin. Another thing that we need to do to prepare for to prepare the twin is to initialize the residual life. Right. So once we know how the rubber tip deforms under load, then I guess the question is before you do any actual cycles, if you have a standard load case, what would be the hypothetical fatigue life of the rubber tip under that standard load case. In this case, we're going to take 1,000, actually 250 pounds is kind of the rated load of the pogo stick. So we'll take that as the standard load case for the pogo stick. That translates into I believe it's 1,100 newtons of vertical force with no side force. And so what we'll do is we'll run a simulation with just a single bounce for that load case, and we'll use that to present the initial residual life, which you can see here plotted on this contour plot. Now, the Endurica CL solver uses a procedure called critical plane analysis, and this integral that I've mentioned, where we integrate the size of the crack, that calculation is iterated over every possible orientation that a crack might take, right? So within any given single element, a crack potentially could occur in a number of different possible orientations. And what we do in our fatigue calculation is we calculate them all. You might say that the critical plane analysis is kind of a Murphy's Law type of principle, in that we're looking for the crack that's going to grow the fastest, and that's the one that we predict as controlling the fatigue life, right? So here's the workflow for updating the digital twin after we've set everything up and initialized the residual life. The guy on the pogo stick is jumping. There's strain gauges here that feed into a file. We record those. We pass those on to TrueLoad, where they're converted to X, Y, and Z loads on the tip of the frame, which we can then feed into our Endurica interpolation engine and convert the X, Y, and Z loads into strain history for each finite elements in the model of the rubber tip. And once we've generated the strain histories, we can feed those into Endurica DT, where we can update the damage state for each element and finally present those. This is a lightweight dashboard that I'll show here in a minute. We can present the residual life at the current state, and we can also show some graphics showing the distribution of damage that's been accrued in the part. And at that point, then we can hit the update button and receive another file full of this information and start the process again and go round and round updating.
What I'm going to do now is just to give an initial test, let's do one standard jump, right? And what we would expect when we do one standard jump is that the residual life should decrement by 1 unit. So let's go ahead and do that. To do that, I'm going to hit the update button, and I'm going to go and find the CSV file that has the X, Y, and Z load history as a function of time. It's, in this case, a file called standardjump1.csv. I'm going to open that. Here we're plotting out the history. In that file, you can see the Y component of the load. That's the vertical direction. Y goes from 0 to negative 1112 newtons back to 0. So there's our 250 pounds. You can see that our residual life has decremented from 178.24 to 178.23, right? So we went down by 1 standard jump on the residual life. And go out and grab the data file that has 10 jumps in it. Again, no side force. You can see the green here. That's the FY 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So those are the 10 jumps. You can see that the process has just updated the residual life, and it dropped by 10 cycles, just like we would expect. So here we're feeding in standard jumps, and we're seeing that the metric of projected future hypothetical standard jumps is decrementing in the amount that we would expect.
So what about some real jumps? Okay, what about getting some of my real data, run it through?
Yeah, sure. Let's go ahead and we'll do your first jump. Bring that in, and we'll go ahead and run it. There's your first jump. You got 1, 2, 3, 4, 5, 6, 7, 8 jumps. None of these jumps were up to the full load, right? So at most you've got 828 newtons of downforce. So you're kind of, kind of lightweight compared to the standard.
I don't weigh 250 pounds.
Taking small jumps, little bunny hops.
Yeah.
So in all, that decremented the residual life by 2 standard jumps. And it's starting to, I guess if we were to keep doing this particular one over and over, I think we'd see this distribution starting to round out, because mostly this is vertical load. Your side forces on this were very small. We'll grab one of your, I forget
number which 7. Number 7, I think, is I was finally getting good by number 7.
I'll grab the PV one here.
Yeah.
So this one has what, 100 data points in it?
About, yeah, something along those lines.
So there you go.
You can see that I'm able to withstand the pogo stick a little bit more and keep my balance.
Right. So here you're almost hitting the full load, almost not quite the full standard load, but certainly you're getting 1, 2, 3. You're getting a bunch of these.
Yeah.
It ends up adding up to 5 standard jumps of damage is kind of what you ended up doing here.
Yeah.
So
well, it does more damage to me, I can tell you that. Okay. Well, that's very cool. So
yeah.
So just from some strain gauges, we can run loads into your structures here to get rubber in your digital twin. That's really cool.
Absolutely. Yep. Yep. So.
Okay, great. Well, super well. This was a fun project. A good way to spend our pandemic lockdown here to go through and kind of have this kind of cutting edge little technology between the two of us here.
This has been a lot of fun. Okay. Thanks, Tim.
Okay, great. Thanks, Will. Bye.
All right, bye.
Okay, so that wraps it up. Okay, so we're is a good paper between Will Mars and myself showing basically being able to turn any structure into a load transducer and then using those loads for doing fatigue calculation. But once you've got loads, you can do any design work you'd like. You know, so you could do fatigue calculations, you could do design and deflection calculations. It really doesn't matter. Okay, well, Santosh, I think that wraps it up for this evening.